Entropy shapes everything around us, from the way your coffee cools in the morning to the way stars burn out across the universe. Yet most people hear the word and think it simply means chaos or messiness. But entropy isn't chaos. It's probability. It's the quiet rule that guides why things change, why structures decay, why energy spreads, and why time itself moves forward. Today, we're going to peel back the mystery behind entropy and show you why the universe naturally shifts from order to disorder. Not because it's breaking down, but because there are far more ways for things to fall apart than to stay perfectly arranged. And once you understand that the entire unfolding of the cosmos starts to make sense, entropy, it's one of those words that shows up everywhere: physics, chemistry, biology, information theory, even in conversations about life falling apart. People use it to describe chaos, disorder, randomness, and the natural tendency of things to break down. But what does entropy actually mean? Why does the universe seem to prefer messiness over order? And why do things fall apart in the first place? The truth is, entropy isn't chaos. It isn't destruction. It isn't some force that pushes things toward ruin. Entropy is much simpler and much more fascinating, because entropy tells us something fundamental about how the universe works. Not why things break, but why they are overwhelmingly likely to break. Not why order fails, but why disorder wins. Today we're going to explain entropy from the ground up, what it really means, why the second law of thermodynamics governs the direction of time, why hot coffee cools down, why ice melts, why life needs energy, and why the universe is slowly drifting toward a final cold, quiet state. And by the end, you might see entropy not as a destructive force, but as a story about probability information and the natural unfolding of the cosmos. Let's start with a simple question. Why do things fall apart? Imagine you have a perfectly clean room. Everything is stacked neatly, the floor is spotless, books are aligned straight, and your desk is clear. Now imagine leaving that room alone for a month. No one enters. No one moves anything. And yet dust will settle. Air currents will shift objects slightly. Temperature changes will cause materials to expand and contract. Over time, the room becomes slightly more disordered. The question is why? Why does the universe naturally drift from neatness to messiness? The answer is entropy. But entropy isn't messiness itself. Entropy is the number of possible ways the particles in your room could be arranged. When things look orderly like a clean room, there are only a tiny number of possible arrangements that count as clean. But when things are messy, there are millions, trillions of ways they can be arranged and still look messy. So entropy isn't about things getting worse. It's about probability. High entropy states are simply more likely. Let's break this down more clearly. Entropy is a measure of how many microscopic configurations correspond to the macroscopic state you see. If you look at a glass of iced tea, you see the tea and the ice cubes. But each of those ice cubes is made of trillions of molecules. Those molecules can be arranged in an unimaginable number of patterns. And when the ice melts, those molecules are free to move, mix, and rearrange themselves in far more ways. There are far more possible states for liquid water than for solid ice. That increase in possible states, that increase in the number of configurations, is what we call entropy. The second law of thermodynamics simply says, the total entropy of a closed system tends to increase. Not always, not instantly, not in every small moment, but statistically, overwhelmingly, inevitably. Things move toward states that have more possible arrangements because there are so many more of them. This leads us to the arrow of time. Why does time move forward? Why do we remember yesterday but not tomorrow? Why do glasses shatter? But shattered glass never spontaneously rebuilds itself. Because going from low entropy to high entropy is easy. Going from high entropy to low entropy is incredibly unlikely. Not impossible, just fantastically improbable. Picture a glass hitting the floor. When it breaks, each tiny shard scatters randomly. There are billions of ways to be scattered, and only one incredibly specific configuration that counts as unbroken. The laws of physics do not forbid the glass from reassembling itself. They just make it so astronomically unlikely that it might as well never happen, even if you waited longer than the age of the universe. That's entropy. The universe moves towards states with the greatest number of possible configurations. That's why things cool down, break apart, diffuse, dissolve, and decay. But entropy is easily misunderstood. Many people think entropy means chaos. But that's not quite right. For example, a deck of cards that's perfectly shuffled has high entropy because there are many possible arrangements. But a deck sorted in order has low entropy because there are only a few arrangements that look sorted. Yet neither is chaotic in a visual sense. They're just more or less likely states. Entropy is not chaos. It's probability. Let's look at some everyday examples to ground this idea. Take a cup of hot coffee. When it sits on the table, heat slowly flows into the surrounding air. Why? Because energy tends to spread out. There are far more states where heat is evenly distributed than states where the coffee stays hot and the air stays cool. Heat spreads because mixed energy states are overwhelmingly more probable. Or consider an ice cube melting. Solid ice has molecules locked into a rigid structure, few possible arrangements. Liquid water allows molecules to move freely, many possible arrangements. So melting is simply moving from a low entropy state to a high entropy one. Or imagine stirring cream into coffee. At first, the cream forms beautiful swirls, low entropy, because the arrangement is special and unlikely. But as the liquids mix, the swirls fade. The mixture becomes uniform. And that's a state with far more possible microscopic configurations. It's the natural, more probable state. Now, entropy doesn't just apply to physical objects. It affects biology too. Life is a constant fight against entropy. Your body, your cells, your DNA, they all require enormous amounts of energy to maintain their structure. Think about it. Your heart pumps your cells, repair damage, your enzymes, fix errors in your DNA. Your body transports nutrients, burns calories, and produces heat. Every one of those processes increases entropy somewhere else. Life creates order locally by increasing disorder globally. Every time you eat food, you're importing low entropy structures into your body. You break them down, extract energy, use it to build and repair your own structures, and release the waste as heat and byproducts. Living things don't defy the second law, they operate because of it. Without entropy, life wouldn't exist. Now let's zoom out to the ultimate scale, the destiny of the universe. Entropy applies not just to cups of coffee and living cells, but to galaxies, stars, and the entire cosmos. Right now, the universe is full of temperature differences, energy gradients, and structures that can do work stars. Burning fuel planets, radiating heat, black holes generating jets. But over tens of trillions of years, entropy will rise. Stars will burn out. Matter will decay. Energy will spread thinly across space. Eventually, the universe will reach a state of maximum entropy called heat death. In heat death, everything will have the same temperature. All the energy will be evenly spread. No gradients, no movement, no work, no structures. A perfectly balanced, perfectly uniform universe where nothing interesting can happen. This isn't destruction. It's equilibrium. It's the point where entropy has no room to increase further. A quiet, cold, still cosmos. Entropy also has a surprising connection to information. In information theory, entropy measures how much information you lack about a system. A messy room has high information entropy because you have no idea where anything is. A tidy room has low entropy because everything has an assigned place. A shuffled deck of cards contains more entropy than a sorted deck. This idea unifies physics and information. Both describe the number of possible states and how they evolve. In fact, modern physics suggests that entropy and information might be two sides of the same coin. In other words, when entropy increases, information about the system spreads out or becomes inaccessible. So, what does entropy tell us about time? Time moves forward because entropy increases. The future is the direction in which things are more disordered and more probable. The past is the direction in which things were less disordered. We don't remember tomorrow because tomorrow corresponds to a high entropy state with millions of possible configurations. We remember yesterday because it was more specific, more ordered, more improbable. In simple terms, time is the universe moving from improbable states to probable ones. The second law doesn't force anything to fall apart. It simply says that states with higher entropy states, with more possible arrangements, happen far more often. Let's bring this all together. Why do things fall apart? Because there are vastly more ways to be fallen apart than perfectly assembled. Why do hot things cool down? Because heat likes to spread. Why does ice melt? Because liquid water has more possible arrangements. Why do living organisms need energy? Because staying ordered requires constant maintenance. Why does the universe move forward in time? Because entropy increases. In the end, entropy is not the villain of physics. It's not the destroyer of order. It is the storyteller of the universe. It explains why things change, why time flows, why life exists, and how the cosmos evolves. Entropy is the quiet statistical truth behind everything that the universe is always exploring, the most probable states available to it. And because there are so many more ways for things to be scattered than to be perfectly arranged, that's where everything naturally ends up. You don't need to fear entropy. It's not working against you. It's simply describing the direction things tend to move. It's the engine behind aging decay, mixing melting and heat. It's also the invisible backdrop for emergence complexity and life itself. So the next time something falls apart, a glass breaks, a room gets messy, your coffee cools, or your day feels a bit scattered, remember that entropy isn't the force causing it. It's the probability that makes it overwhelmingly likely. It's the universe following its most natural, most probable path forward. And that's what entropy really is. Entropy isn't the enemy we often imagine it to be. It's not a force tearing things apart, or a sign that the universe is somehow running down. It's simply the statistical heartbeat of reality, the natural tendency of things to move toward states that are more probable. It's the reason time flows forward, the reason life needs energy, and the reason the universe evolves the way it does. And even though entropy guarantees that everything will eventually spread out and cool down, it also guarantees the moments of complexity, structure, and beauty that rise along the way. If you enjoyed this explanation and want to explore more about how the universe really works, feel free to subscribe and join us for the next journey. Until then, stay curious and remember that even in a universe ruled by entropy, there's still room for order, meaning, and wonder.